Again, you're the one filling the gap. Okay, so how do we get that? And so, Austin, if your question is right, we use the idea, we basically calculate the entropy change using entropy. That's how this come in. So if you're like, oh, how do we get from here to here? This is what this class is about. So you go back, either review the notes, and if you actually already know my pattern, this will be one of those key points that I want to make sure you get it.
So then that would be in equilibrium or something where delta G equals 0. That's when entropy equals like enthalpy over.
At this moment, we can consider the heat change is so tiny amount, so the temperature of the system surrounding is not changing. So we can use the T directly. Now, that's one assumption we made. The other thing is because the heat change step is so tiny, we can consider them to be reversible. The second point. The third point is since it's under constant pressure, so therefore the heat exchange can be traced by the state function enthalpy. So with those three things in mind, you can actually make the transition from here to here if you introduce that. Any questions? In fact, no, I did not prepare. I was just kind of talk as what in my head. So this whole thing could also be modified according to you guys' question. My goal today is try to work with you to refresh what we get.
So you need a constant pressure to do the delta S equals negative delta H over T.
You need it to be under constant pressure to basically make the equivalence of this statement to this statement. The reason is when you do that, remember when you apply these to calculate the entropy change of the surrounding, you want to reflect the surroundings entropy change by your system's entropy change. There is a heat got delivered exchange between the system and the surrounding, where that heat can be shown as changing of the system state through the enthalpy. But for that to be true, we already stated earlier.
What about the temperature? Why is temperature?
Exactly. Why is the temperature? Well, because for calculating the minimal step, that T has to be, otherwise we would have to do this, and that gets to be complicated. And then we are talking about a tiny step. So basically, this you can think of this as a tiny step. We're just using the tiny step whether it's going to go or not. But we approach this usually, when we talk about model situation, we try to introduce the concept with something that's less tractable. Obviously, later on you can calculate delta G by integration as well. But when you introduce the concept, it's like when you do entropy change, generally speaking, this is actually not applicable. When you add heat, how do you not change the temperature? It's just not true, right? But in the vast universe or system, you can assume this is true. Or if the heat change was so tiny compared with the system's size, and then you can think of this as, it's like when you do a tiny step when we earlier talked about the reversible expansion kind of thing. It's like, what do you mean by reversible? Reversible means internal pressure and outside pressure to be equal. Well, then how do you move the piston? So it's just kind of weird kind of a situation that you only theorize in the model system, but you actually, it was kind of a little counterintuitive in reality. So this is true here. So when you actually make a step so tiny, you can assume the temperature not change, where a small amount of heat is get delivered. Now in this case, so the constant temperature, constant pressure made us jump from the H. So you basically can calculate this guy using the delta H system. Right, so that's how we got it, basically. Now, again, I didn't plan to put it in here, but so the surrounding entropy change, everything get calculated by what's happening in the system. So that way, we cannot worry about surrounding anymore. Then we just focus on what this system state function change to predict what that thing is going to be spontaneous or not.
You said to get from the delta S ISO be greater than 0, to get from that one to the delta G, we needed to have constant temperature, constant pressure, and then we considered the third thing.
Oh, we actually we assume it's a tiny small enough, so it's reversible process. But since it's a state function, normally you can say, hey, I want one tiny reversible, and then I go to another tiny reversible step. So except that when you talk about that, it could be temperature 2. And then when you go to the next one, you go to temperature 3. So, but in the end, it's like we're doing here. When we do this, the reason you can do this, when you have a beaker, you heat it up, you don't do this. Like you go temperature 1 and 2, and you find out the total Q equals CV is T2 minus this. And you can't do T, and what's the T going to do? You can't do that. Right? But you can always think of, oh, I went from here back through T plus delta T, we keep going T plus, T1 plus. And then that's end up to be this, guys. Yeah, makes sense? So this will be the kind of thing I want you to fill out. I have to save the board here because I'm going to leave this one because we have a lot of stuff to fill in this board. So. But if this is more important, we can actually try to finish up even in a second. But let's try to finish the framework discussion today. So, that's all good. So now, by the time we get to here, we really establish the fundamentals of what we needed. So we start talking about how we can manipulate a process by experimentally. So yeah, you can always do this. So you realize delta G will be a good way to predict if something is going to be spontaneous or not. But we also want to achieve the ability to use this to alter the system's behavior. That is, make them go or not go or shift the sense around. And before we end up using this extensively, we actually used this to describe what we call a phase transition. So in that case, but everything else we end up, we can manipulate a system's G and P, we can actually manipulate the system's spontaneity if they're changing. So I think the phase transition was something we end up apply this, but in that process, we actually realized we can alter the phase diagram by a this is the key component. So to get, then you go like, oh, how did we get this? Again, this is something you're supposed to fill the gap. Because today we try to use 40 minutes to cover a whole semester. So I won't be able to do that, but I want to tell you what did we do? What was the point of getting here? So the phase transition we actually talked about, like when you reduce the pressure, or remember like one of the exam questions, we try to convert the diamond to graphite. Those are the examples we can make a what appear to be non-spontaneous reaction to become spontaneous. Well, how? Well, because we can alter the Gibbs energy change of a process by manipulating the Gibbs energy on each side. Now, I realize one of the major confusion oftentimes is like, wait a minute, Professor Chen, you just said that everything has to be constant temperature, pressure. How are you going to use temperature, pressure changing to then still use this? So I remember one of these questions came up in the past. Now I'm going to ask you if anyone knows how to answer that question. Let's say I remember we have Clausius-Clapeyron equation. If we actually manipulate it, yes, Eric?
Because it's the state function.
Not quite. Because we actually remember what the best example of phase transition application of this is that any liquid, when you increase its temperature, its vapor pressure will increase. That's the result of application of this. Now, but oftentimes you still just get like, when too many times, people just kind of, students actually often get confused. Like, what? You just said that this whole thing has to be constant temperature. Why you all of a sudden start talking a lot about temperature, pressure, and altering the system?
Because delta G is looking at like the difference between the two states versus dG, you're altering the like molar Gibbs energy of that state. Is that right? So you can
Probably, I think that's
T&P.
probably what you mean. Yeah, that's basically what I was looking for the answer. So if you remember the phase diagram, so this temperature pressure meaning the stop, the end point has temperature pressure. If I move this into I still apply it. So this temperature pressure constant means the process in the beginning and end has to be temperature pressure. But I can alter the whole system into a new temperature pressure as long as this is where oftentimes students get confused. So if you look at the phase diagram, if you have a temperature pressure, of course at a certain temperature pressure, there's a pressure. But if you go to another temperature pressure, then gets another temperature. And this new temperature pressure changing is basically you are manipulating the Gibbs energy of the two phases. And then because the two phases temperature pressure difference different, so they have different slope. That's how we are able to change the graphite into diamond by applying pressure, because they have different density. So therefore, the slope of the change of Gibbs energy of each phase could be different. So therefore, when you apply enough pressure, eventually the one that actually always have higher or lower Gibbs energy will catch up the other one. Then the spontaneity balance will tip over. Then what is normally non-spontaneous process, like graphite become a diamond, will become spontaneous when it gets high temperature. So important to keep that. But it turns out this is something we use a lot. Okay, here it's all good. So we have gone pretty good up to this point to introduce Gibbs energy, to predict it, and we actually introduced one very common application is we realize Gibbs energy can be manipulated by pressure and temperature, and this turned out to be very useful later on. Okay. Good. What time is it? All right. So I actually forgot what we did in detail, but I'm just talking about anything come to my head. So here we also realize that when we talk about phase transition, we realize the more useful quantity was instead of compare the total Gibbs energy of a process, we find out oftentimes the Gibbs energy when used in the per mole is much more useful to describe whether some matter is going to go from one state to another state. So this is when we first introduced molar Gibbs energy. So basically, that is the total Gibbs energy divided by the number of mole you have. So when you compare a phase diagram, you don't have to worry about, because you could have a tiny little ice to be equilibrium with a big ocean. They'll be at equilibrium as long as the molar Gibbs energy of the water in the ice form and the liquid form to be equal. So that gets you away from worry about the size of the scale of each of the phase. Now this this basically led us to use to describe a phase diagram and all of this, but we realized that Gibbs energy is not limited to just describing pure substance. So this is when we made the transition into mixture. So when we get into the mixture, And so the molar Gibbs energy, we give it called partial point molar Gibbs energy, but it's still kind of considered to be okay, I know we tried to use some partial derivative. We didn't want to do that, but I want to say something that is, there's a, I don't want to write the mathematical formula, but basically it is based the now it's related to molar Gibbs energy. You can conceptually think it is molar Gibbs energy, except unlike molar Gibbs energy of a pure substance, it's a constant. The partial molar Gibbs energy not only is different from the pure, its value also changing according to its concentration. Then you will go like, wow, how did we get that? Again, you need to fill the gap. We actually demonstrate this point. We have shown that when you take two ideal gas, we went back to the old example. You mix them. Nothing else changed. But we know that process is spontaneous. So we know the Gibbs energy change was negative. And then we know there's no delta H change. So basically we went back to find out, we realized when the ideal gas was pure, it has a molar Gibbs energy. But when the ideal gas was mixed with something else, its molar Gibbs energy get degraded. Now we can mathematically prove that point. Then you go like, how do I do that? Well, you got to fill in. So basically using ideal gas, we find out, we now decide to use mu. Basically you can call these partial molar Gibbs energy, and we find out it's related with pure. And this ideal gas molar fraction in the mixture. Well, the backdrop of this is we knew eventually when we go into our electrical system, we will be talking about mixture. So then you end up, okay, how do we get there? Well, this is when any of these gap step is where you need to review. Okay. So this is provide the pathway for you to what topic you want to review on. Okay, so it was like, okay, we're really not happy with just stay with gas phase, and we decide this idea could also be used with solution. And then we show this is true, yes. Except in this case, we can actually use this as a concentration, and obviously you can take it, whatever your reference point, concentration as a compared point. So virtually your concentration was divided by the unit concentration. So if you use 1 molar of your species concentration as a reference point, that 1 molar will be divided, and that's why you lose the unit. So, and here we talked a lot about how later on equilibrium constant, this and that, they don't have dimension. So I'm going to speed up a little bit here because I just realized because my purpose today is really try to lay out the framework. So when you go back, you know what we did. So, and this is all good, but you go like, every arrow is a question. Probably someone that has arrow is where you need review. Okay, how do you get that? And you go like, so very quickly, anybody, how did we make this transition? What was the law we used? Root's law. So and then how do we do that? You want to go back to review the process. Obviously, along this, there's other side point. I don't have time to review here, but you want to remind yourself about like, okay, what is we mean by activity, activity coefficients, And later, we can talk about ionic case, what is the active coefficient and the mean ionic coefficients, how the ionic strengths, those are the things that are all serving to expand the application of this. Because when you talk about ideal solution, this is ideal solution, and everything is supposed to be ideal, but in reality, the solution, the concentration, not only the molecule kind of associate each other, so they don't really behave as purely free, so that's why we get them activity coefficient, we introduce the mean activity. And then this is even more so in the ionic solution, this becomes very significant. That's why we even introduce ionic strength concept. How do we use ionic strength to calculate the ionic mean ionic coefficient? So these things are required for you, but they are not conceptually stand out. These are the things that we try to use this in a practical situation. So you also are supposed to review this, right? Now, okay, after all of this, in fact, even up to this point, before we get to ionic case, on this one, all of a sudden opened up another aspect of application. So we're good to use this to describe the pure substance, the temperature pressure relationship. But here, all of a sudden, we realize we can combine all three parameters to describe a absolute very interesting phenomenon, which is we realize the Gibbs energy or molar Gibbs energy or chemical potential can be affected by concentration. Then recall, we can also manipulate the Gibbs energy by temperature or pressure. Right, so just these three things allow us to understand many interesting phenomena. So if you recall a few, we still use phase transition first to demonstrate this point. We end up using, we talk about the collective property, the melting point, change, and boiling point, and osmotic pressure. Now, all of them are an interplay of molar Gibbs energy or chemical potential by concentration, temperature, and or pressure. Then you go like, what is that? Well, again, you're supposed to review it. Well, just as very simple, I don't have time to ask the class, you go like, oh, let's just go back to phase diagram. When at equilibrium, ice and water gets the molar Gibbs energy is the same, but if I add stuff in the water, the chemical potential of the water will drop. It will shift the equilibrium, but I can compensate that by changing the temperature. So that's how the boiling point, the melting point gets in. Similarly, boiling point affected that same way. And pressure is the same. If you have two solutions, one solution high concentration, the other one either pure or low concentration, the chemical potential is different. So the water tries to rush from high to low, and then you can compensate that by pressure. And that's the result of osmotic pressure. Now, conceptually, that should be in your head, and then quantitatively, you want to look back how we did it to show how we can estimate or calculate the osmotic pressure and the change in boiling point and so on. Oh, only have 2 minutes left, so wow, I have to really fly through everything. But actually, that's okay, because I'm not planning to review the kinetics. So by the time we get here, we're good. We're almost done. In fact, the rest of the, so we find the chemical potential is all useful in the phase diagram, but in reality, at the end of the day, we still want to talk about chemical reaction. So, so we basically found out that for any and this is the true application of this concept to chemical reaction. And then you go like, how do you get that? Well, it's a combination of this guy and this guy. for a process to be at equilibrium, the reaction Gibbs energy would be 0. The reaction Gibbs energy can be expressed by each component's molar Gibbs energy by under the stoichiometry ratio. Now, if you express that correct, and then you realize each chemical's molar Gibbs energy is related to its concentration. So, when after you put all the picture together, you will go, yeah, that's right. When the chemical at reach equilibrium, its concentration follow the definition of the equilibrium constant would follow this rule. That is, they must be a constant related to the standard state Gibbs energy. Now, how do we get this? You need to review. I was planning to have more detail, but I just realized I shortened it into 1 minute. But I don't want to complete this. Okay, so that's for any generic reaction, right? But then we're like, wait a minute, what about the redox reaction? Well, it turns out for redox reaction, we can even make it even more useful. That is, for now, this reminds me, I forgot to say something earlier. That is, the Gibbs energy change corresponded to the non-expansion work, and we used this concept. Well, we established this concept earlier. We tried to derive it, but we didn't really use it. But by the time we get here, we used it. That is, for a chemical reaction, if we use the Gibbs energy, we can actually describe molar chemical potential. We can describe where the chemical equilibrium constant coming from. So we were able to relate the Gibbs energy of reaction to why the concentration of the product and the reactant, the ratio, follow a rule. And that rule is confined by the requirement of Gibbs energy for that reaction to be 0. And for that to be 0, for that to be related to the concentration, you're going to use this. So that's how all of this is reflected on the discussion of the chemical equilibrium. And the electrochemistry is another aspect of usage of the Gibbs energy to describe a redox reaction in the context of a battery where you have. So this is virtually the basis of all the electrochemistry we talked about. Whether it's a Nernst equation or whether it's a redox potential, we talked about it. Those details you need to fill in. But you can see this is how we got here. By the time we got here, the electrochemistry, we virtually finished everything we want to cover in terms of the thermodynamics part of it. The kinetics part, we just finished, so therefore I don't want to spend another lecture to review something we just finished. Virtually, if you think about it, a few main points is that the rate law, how do we express it, what we mean by the rate constant, and that's something, it's a standard introduction. The important concept there is how rate constants temperature impact on the rate constant allowed us to introduce the model of transition state and activation energy. So those two concepts coming from the temperature effect on the rate constant. That was one aspect of, if anything about kinetics I want to remind you review. The second aspect is to deal with consecutive reaction, we used what we call a steady state assumption, and a special case of steady state assumption is this pre-equilibrium. So that's the second main point we spent some time to show you, because that's a very important skill for you to deal with chemical kinetics. And the most obvious application of that skill is when we talk about enzyme kinetics. So we basically had them show, right after we discussed the steady state, we showed how to apply steady state in analyzing enzymatic reaction. So I'm not going to write that part up because we just done. Now this board, it's kind of weird because it was so small, but that's really what we did in the whole semester. Isn't that amazing? So we just use this as guideline and follow the lecture notes. PowerPoint is important to follow, and the supplemental video has many details on some of the errors, because the error that I think is important, if you actually kind of like, oh, what do you mean by that? So some good place is look at the supplemental video, especially how we made the transition to this, to that, and so we have total like 36 lecture, but every 2 lecture we have 1 supplemental video. So the supplemental video, what I was trying to do is provide, every time when we try to introduce an important concept, I make a supplemental video for it. So the way to study for the final is use this outline I had today. I'll post this video as well. If I had myself photograph in it, but at least you'll hear the recording of the voice, so you see what I said. And then look at the PowerPoint and supplement window and the homework. Because homework, I know there's some disconjunction here, but they're supposed to be supplement to the material. Because I emphasize concept a lot. Those homework allow you to practice on a subject by subject, a specific manner. And what I'll do is in the weekend, I'll post the old final exam for you to look at, as well as a set of practice questions we'll go over on next Monday and Wednesday. All right?
Well,